Good afternoon, and welcome to hand-wavy chemistry. There's platinum in cars, and I'm not just talking about small trace amounts. I'm talking about roughly 5 grams of platinum in every gasoline-powered vehicle. And that platinum is located between the engine and the tailpipe inside of a device known as the catalytic converter. Its job is to convert potentially noxious, harmful gases into more benign alternatives. But before we discuss how it does this, I want to first discuss a different chemical process that also uses a platinum catalyst: the hydrogenation of alkenes. Alkene is the term that chemists use to describe a carbon-carbon double bond. And when I say the hydrogenation of an alkene, what I am describing is the addition of 2 hydrogen atoms across that double bond to convert it to a single bond. This process is used in the production of margarine. We start with an oil that contains multiple double bonds. It's why it's described as being polyunsaturated. And then we begin to hydrogenate it. Add hydrogen across those double bonds until it begins to solidify and turn into something more like a fat. But if I were to take a flask of vegetable oil and bubble hydrogen through it, I could keep bubbling the hydrogen through for months and nothing would happen. The activation energy required for the reaction to occur under those conditions is just too high. We need a catalyst. A catalyst introduces a new reaction pathway with a lower activation energy. One metal that can catalyze this hydrogenation reaction is platinum. So let's talk about how that works. We begin with our platinum surface. Our alkene comes down and adsorbs onto the surface of the platinum. It does this by using those electrons in its pi bond, the double bond. Now, I'm going to redraw this slightly with bonds directly from the carbon atoms to the platinum. This is not to say it is a more or less accurate representation of how the alkene interacts with the platinum, but it is simply done because it makes it clearer to see what happens next. And that is, our hydrogen arrives on the scene. And it comes down and it also adsorbs onto the surface. But in this case, there's no pi electron system to attach through. So instead, the 2 hydrogen atoms detach from each other and are now separately attached to the surface of the platinum, free to wander off on their own. Let's see what happens when the first hydrogen approaches our alkene. You can see that as it comes in, it begins to bind to the carbon. The alkene lifts up from one end of the platinum, and now we have a CH3 group present. The other end is still bound to the platinum, however. Next, the other hydrogen comes in and interacts with our hydrocarbon. It breaks that final carbon-platinum bond, generating our reduced alkane. Now, free from interaction with the platinum, it can float off and go about its merry way. One piece of evidence that supports this type of mechanism is that we observe the hydrogen atoms to always attach to the same side of the double bond. So they must both be coming in along the platinum surface. Now let's look at the catalytic converter and consider how it handles carbon monoxide. The process is very similar. Carbon monoxide and oxygen adsorb onto the surface of our catalyst. The oxygen atoms split and separate from each other. They are then able to go and form bonds to the carbon end of the carbon monoxide, forming carbon dioxide. Carbon dioxide is less attracted to our catalyst surface than carbon monoxide was, and so it can come off and leave, and the process can repeat. Notice how the surface of our catalyst is not actually used up in any way during this reaction. Catalysts lower the reaction pathway, but they themselves are not consumed during the reaction process. Another potentially harmful gas produced in internal combustion engines that is able to be removed by a catalytic converter are nitrogen oxides, nitrogen monoxide, and nitrogen dioxide. Now, I'm not going to show another diagram of the various nitrogen species adsorbing, rearranging, and then desorbing, because there are a range of different reaction pathways involved with the reduction of nitrogen oxides. Instead, I want to simply highlight that our end goal product from these reactions is nitrogen, which already makes up most of our Earth's atmosphere, so clearly is not harmful. Throughout this video, I've kept highlighting the idea of the platinum catalyst, but actually nickel, platinum, palladium, and rhodium are all capable of catalyzing these types of reactions. And in fact, the catalytic converter inside of a car is a blend of platinum, palladium, and rhodium. And for the industrial production of margarine, a nickel-based catalyst is used. So how do chemical engineers determine which specific catalyst is best suited for a particular application? Well, that is a story for another day. I hope you have enjoyed this video, and if you have, please make sure to like, subscribe, and share it with your friends. And if there is a topic you'd like to see covered in a future video, please put it down in the comment section below. Thank you, and I hope you have a wonderful rest of your day.